Okay, so we're in business. So for those who don't know me, I'm Ed Blockley. I lead the Polar Climate Group at the Met Office. Hadley Centre, we developed a sea ice model component, which is used for climate, but it's also used for all forecast scales, hence my cameo earlier and the talk. But I'm going to be talking primarily about the challenges for the model development for our climate model. And firstly, you can see the first challenge we have is this is the Met Office slide. There's no sea ice. So one of the big challenges we have is that it's not considered the most important thing in the world by some. So I'm going to talk very briefly about climate modeling, CMAP 6, just to say what gets done internationally, and then I've got some sort of anecdotal evidence and stories about basically things that have made my life difficult over the last 10 years or so. So firstly, you've heard about CMAP a few times. I'm going to sort of spell it out a little bit more, well, literally here. It is the Climate Model into Comparison project, or couple model in comparison project, phase 6 is CMAP 6. So what do we do in CMAP 6? A load of people run a load of climate models. But what happens is you have this pre-industrial control. Everyone runs a pre-industrial control. It's 1850, constant forcing. And from that, we have 3 sets of climate experiments. We have this abrupt step to 4 times CO2 here, illustrated in red. We have a transient continuous increase of 1% per annum of CO2, which is green schematic. And then we have the historical runs, which Marika's already talked a bit about, which have real forcing that is, let's say, motivated by observation. And this is increasing greenhouse gases. There are scenarios formed from these. Each of these, you'll do this, have to do this with every ensemble member, every model. And then there are about 50,000 different MIPS at CMAP 6. I'm not going to mention here. So when you do your ensembles, you've got to do this a load more times. And generally what we would do is we spin up our pre-industrial control. That takes a lot of time. And then you run the pre-industrial control and you spin all these bad boys off at various different periods. And then we get on to the joy of the scenarios. So this is the matrix on the left of which scenarios for CMAP 6 are developed. They're shared socio-economic pathways. There's potential for loads in that massive matrix. The blue ones are the only ones that have been chosen, and the dark blue are the sort of tier 1. So these are all of them on the right, showing the different CO2, total CO2 emissions in all these scenarios. So there's a lot of them. And then there are models. There's a lot of processes in the model that unfortunately for us are not CI. In the UK, we ran 3 models for CMAP 6, 2 different resolutions and 2 different complexities. So low and medium resolution, and then this is the low resolution with all the Earth system processes as well. I'm not going to talk about high-res MIP. There's at least another 6 different resolutions that we ran for high-res MIP. So this is mostly the point I'm trying to make with these red underlined bold things, is that it's expensive, right? So the models have to be cheap, the models have to be efficient, we have to be a bit sensible about what we put in and why. So every model to get in and run these scenarios, you've got to do all the other stuff. You've got to run the DEC, which is the pre-industrial control. You've got to run the 1% and the 4 times CO2 documentation as well. Lots of diagnostics. There are papers and papers of diagnostics. So this all basically means there are lots of trade-offs here related to things like resolution, complexity, and ensemble size, which are very, very difficult decisions to make. And then you have to decide what MIPS, what scenarios you can run, what MIPS you might contribute to, and then what diagnostics you can actually afford to calculate online and store. We have several petabytes of CMAP data from this last set alone. And then also there's often competition for resources between all the components. And yes, a spoiler alert that sea ice very seldom wins. It's the poor younger brother of the ocean, which is the very poor brother of the atmosphere in many cases as far as the resources are concerned. But yeah, sea ice is important. So we've seen that for a few people. So I'm not going to go through this in any detail. We've seen this a few times. It's very reflective, so it makes a difference. And this is an interesting paper I read actually fairly recently, or we read fairly recently, showing the impact of sea ice on climate sensitivity. So they've run with active sea ice, is the black line here, but they've done a couple of control runs, one with a prescribed sea ice, so the sea ice stays the same, all the different climate forcing levels, or one with no sea ice at all. And you get a very different climate sensitivity if you don't have actively changing sea ice, because as Marika mentioned, it's the change in sea ice that's important for the climate sensitivity. That's these black lines here. And you can see temperature change of say 6.5 Kelvin compared to under 5 or even almost 4 for the runs without the sea ice. So this is why we include sea ice, and also why I get told off whenever the sea ice is not perfect in our models. But often, as any sea ice model or climate sea ice model will tell you, the sea ice is normally ruined by the atmosphere or the ocean. And I'm going to give you a few examples of that here. Sensitivity external components. So some interesting snippets. This actually is the impact of changing the pressure in the model just over the Rockies in our model. So we've nudged the pressure over the Rockies, and this is the difference in pressure globally. As you can see, it's the Arctic that gets it in the neck. So it's very sensitive to what's happening over mid-latitude areas, particularly the Rockies. When we were trying to freeze our CMAP 6 model here, this is a time series showing impact on sea ice volume of a very slight bug fix someone put in to the emission of Saharan dust. So this red line has got double the emission of Saharan dust, and the sea ice volume is increased there by, well, I guess it's about 10% of the total. And then we have to retune the sea ice model. Likewise, the difference between the red and the blue here is all based on aerosol tuning. And the sea ice mass balance is just very, very sensitive to all of those things. And this is a more pertinent example. Recent, we've got paper in review on UKSM 1.1. So UKSM is the UKS system model. This grey line is what we submitted to CMAP 6. And it had this monstrous sea ice volume bias in the Arctic, which was entirely driven by aerosol cloud interactions, in fact. And so the difference here in ice volume between this grey line and the pink line, which is UKSM 1.1, is pretty much almost entirely down to a change in the in the dry deposition of sulfate aerosol. And then on top of that, we put in a little tweak to the albedo of snow on sea ice by 2 percentage points, which takes you from the pink to the olive, and actually looks pretty much like observations. Noting even with this 4-member ensemble here, and this is about a 14 or 20 member, there's huge internal variability. So anecdote 2, this is Fram Strait. So ocean, how much the ocean is impacting the sea ice. We did all of our development in this green model, N216 Orca 025, which is a 1/4 degree ocean essentially, with a 60-kilometer atmosphere. And then when we went to develop the lower resolution model, suddenly the ice volume is hugely more. That's this blue line here. And so this time it wasn't the atmosphere. We looked there first, but it was actually, this was caused purely by the ocean. And I'm being asked, oh, well, is the sea ice not functioning at this low resolution? And I say, well, it was made, kind of made for that resolution. So it should be doing what it's told. And of course it was doing what it was told by the ocean. Here's the difference in the 1 degree ocean and the 1/4 degree ocean in heat across Fram Strait. So this is the Fram Strait section and northward velocity. And basically the heat transport is 5 times more in the medium resolution model than in the low resolution model, which is driving a huge difference in basal melting of the ocean year round. And we couldn't fix the ocean, so I had to change the sea ice albedo, which is horrible. Because a lot of the ocean problems that come from this, the fact that just not resolved that straight. You cannot, there's only one grid cell there, it's not enough to get a decent velocity. And that was documented in Till Coolbrod's paper. And I'm going to talk about the black dog of climate model. The internal variability is very difficult, Marika's given a great introduction to some of these problems. This is just an anecdote from when I first started managing people in this group. One of the guys in my team was looking at the impact of snow conductivity. We're hoping to reduce the ice thickness. So we reduce the snow conductivity on the ice, so we get less basal growth in the winter. Easy. Here it's happening. We get less ice volume, that's the red. And he's run this for 50 years and looked at the last 30 years of the run. And I said, okay, well, keep running it. So then he looks at the last 30 years of the run and he tells me, oh, snow conductivity is actually increasing the ice thickness and the volume. I said, are you sure? There's multi-decadal variability. But actually, the even interesting story was that actually he hadn't changed the snow conductivity at all. Changed it in an area of the code that wasn't being used. And these these changes are just bit level perturbation differences in a sort of 80-year climate run. So what I learned that day was nothing to do with snow conductivity, but did learn a lot from that picture. That's why I include it here. And this is something that I wasn't involved in, but David was, I believe, David Schroeder. This is a study that the guys primarily at BAS did with our CMAP 6 model. They wanted to run it on the NERC Archer climate model. And so they've done these runs, and there's some really big differences between the two caused by internal variability. And when you look, if you look at 2 shorter time series, you basically get big differences. We're seeing this at the moment porting to a new supercomputer. A guy came to me, run a 30-year run. He says that the model on the new machine has got more ice in. And I said, are you sure? And it might not be. But the conclusion of this paper is essentially you need at least 200 years to be able to statistically distinguishable sea ice, which is the same model, at the same forcing, virtually on the same machine. We run a Cray XC40 and they run an XC30, different runtime libraries and compilers version. And so, yeah, some of these distances, if you run a 10-year run, you've got differences of about 1 million square kilometers there. So if you do a quick model development and run yourself a 10-year run and say, my change makes this difference to the sea ice, you might not be right. So finally, I want to talk about coupled interactions and feedbacks. This is one recently we've been looking at the sea ice. We made some changes to the sea ice albedo. So we get this model here on the left. It looks a lot more like the observation than did the old one, which has pleased people. And you can see these are the differences from the observations. This is September. But then now the ocean people are complaining that the AMOC is being destroyed. So the AMOC is reduced by about 5 spheredrops in the North Atlantic. And the overturning stream function is reduced. So when you're trying to change your model, particularly the CIS model, everything is interconnected, and you end up just going around in circles for basically the whole time. And it's another one is the impact of this CIS form drag parameterization that was developed in the CPOM group. This is from Michel Sambados's paper showing the form drag schematic. So we got the sails and the keels impact on drag, and Michel shows here considerable, almost 1 meter difference impact on Arctic sea ice thickness. So we run this in the climate model, and we get this difference on sea ice thickness, which is, well, it's near zero, but it is statistically different in a few locations where these hatchings are, but we don't see that difference. And why is that? A couple of feedbacks. So the boundary layer adjusts, and so the sea ice doesn't see the change really, but we do see it elsewhere. So the wind stress curl is very different. Straight off the bat, we expect to see that. Sensible heat flux is different. We do get, basically, we get a decrease in the boundary layer depth in the atmosphere, and therefore less long wave down forcing. And rather interestingly, it needs furthermore looking, quite a large impact in 500 meter ocean temperature, so more than half a degree. In fact, so the impact of the form drag is huge as far as down to 500 meters in the ocean and up to God knows how many 500 meters in the atmosphere, but not really the sea ice. So one has to bear all these things in mind when making changes to the model. And this is my final anecdote, which is I think maybe one of the most severe, and this was recently published by Jeff Ridley and GRL earlier this year. So this is our CMAP 6 pre-industrial control. Bear in mind, it's an 1850 force control. It's not an equilibrium run. A lot of people use it as an equilibrium run, but it isn't, because the top of atmosphere flux is actually positive in 1850. So there is slight warming. But anyway, we get to 500 years, we submitted the CMAP 6. We submitted it, and then we carried on running it. And then a few days after submitting the data to CMAP, we looked at it and we're like, what is going on there? Antarctic sea ice has completely disappeared. And I mean, it was just a fluke that it happened to happen just after we turned our backs and submitted the data. What was happening here, this is ocean heat drift, ocean heat in the bottom, 1,500 meters down to the bottom of the ocean, low latitudes, medium latitudes, high southern latitudes. You can see basically the ocean's taking up heat the whole time because there is a positive top of atmosphere flux. And what happens here is when the sea ice disappears, the ocean, of course, cools, because what's happened is deep convection. And that's what these big red spikes are, deep convection. And the red is actually the Weddell Sea. So we constantly get these Pallinias in the Weddell Sea, couple per century. Not that dissimilar from observations. We're not too worried about that. But then these red ones are basically the whole of the Ross Sea has gone, sea ice, which we don't believe. And it's just basically a burp in the system. So this is 512 years. The full 2,000 years looks like this. So yeah, dropped off there, came back for a bit, and again. And then eventually we end up at this position where we've actually got 20% less ice, Antarctic sea ice, that is. But more worryingly, we've then got a big increase in global temperature. This is global near surface temperature of nearly half a degree warmer. And we've lost that trend as well. But interestingly, also the centennial variability of the model has changed. We've now got very large centennial, this is a 100-year mean, the thick black line, large centennial variation. And what's basically happening is that the southern hemisphere overturning cell has increased in strength. So we've got increased mid-latitude ocean heat uptake, more southward transport of ocean heat to the Southern Ocean and then coming up and reducing the ice. But I mean, this is quite an extreme global feedback. We're actually running this on a bit here, and he's actually looked like it's starting to do these things again. So, yes, makes our job a bit more fun. So just to summarize my sort of praised anecdotal ramblings, first point I made is that the climate modeling is expensive. So the models they have to be efficient. They are quite extensively chosen and planned. We also have to be very careful of internal variability. It makes it very high in the polar regions, which makes it very hard to evaluate model performance or even to make projections. What Marika was showing earlier were vast sized ensembles, and that really is needed. And then just the sea ice is very, very sensitive to what everything else is doing in the atmosphere. In that regard, it's very interesting because it's like in real life. You can see the changes in the global climate, particularly in the Arctic climate system imbalance. You can see those in the sea ice, which makes it an interesting area to work on. But it also means that people change dust in the Sahara and it ruins the sea ice. And then we have to be careful about coupled feedbacks. But together with internal variability mean it's actually very difficult to work out necessarily what change you've made to the model and what it does and why. So with that, I will finish there and ask if there are any questions.
Thank you very much, Ed. Not sure if I feel happy or sad after that. Okay, questions. I know Bruno has a question. Does any best regards to Bruno, any earlier career? Let's say Bruno still early career, but any earlier career scientists in the room? Okay, well, I guess I'll ask a quick question then. So the comments you made about form drag were quite interesting to me. I mean, partly, of course, because I was involved in developing the model. So we thought it'd be massively important because it would couple into the atmosphere and ocean, but it makes very little difference to the sea ice mass balance in your simulations. However, it seemed to be pretty important for the ocean and atmosphere. Okay, I'm not saying form drag is the best thing ever, but I guess what this means is it's sometimes quite hard to know where a development in the physics is going to have an impact in the climate runs. I suppose what should be our guiding principles, those of us who are not running climate models but want to possibly improve the physical basis of them?
Yeah, it's a very interesting question, and the pertinent one is how should one be testing and developing these things? You can't go straight into the full climate model, then you're diluting things, and you might not be able to see the impact of it, or it's different. But if you run it in too much of a toy model, then you can suddenly get real differences when you run it in full model. I don't have the answers, but I mean, what we are doing when we develop our models is we start with a forced ocean ice model, and we do run test cases in a standalone atmosphere model as well. But we're also very keen to put them together fairly early on to see what's happening, and where possible, running couple model with just that change.
So perhaps
for long enough.
So perhaps a note of caution about your only metric of success as being to put it into a client model, because internal variability can swamp out or confuse the signal. Okay, thanks. Other questions? I think we can let Bruno go now.
I was also very intrigued by this. Is it that you're forming more maybe heavy water on the Eurasian shelf and your Atlantic water was pushed up? Did you look at the vertical structure of your ocean? Like, it's really curious to me, like, that you would see this.
Sure, I've not looked at it in enough detail because unfortunately the guy that was doing this work left, and we've had to prioritize other things. But we think it's because the form drag has got an element of oceanic extra mixing. So we think it's this variable drag at the ocean. So previously, before, it was just the fairly basic, simple McPhee style drag. And so we think that there's a lot more ocean ice drag now, and that is causing the ocean heat uptake. I should say this is from a 150-year run. So this is the last 100 years of a 150-year run.
Well, the mic's right near me. I really enjoyed your talk, and especially these anecdotes, which I found fascinating. I have a question about the last slide you had before the conclusions, the last anecdote. There we go. So you mentioned that what happened in the sea ice area was this like buildup of heat in the ocean, and all of a sudden these convective events in a pretty small part of the globe. How come the global mean temperature is so correlated with the sea ice area? Why does the global mean temperature care so much if you have some convection event off in like Ross Sea?
Well, the Southern Ocean, I mean, the Southern Ocean is kind of like the lungs of the planet, right? Yes, it's just really ventilating that heat. So there was all this heat was just in the deep ocean, and basically the deep ocean has just burped it back up into the atmosphere, I think. But then there is an albedo impact. Quite interesting, because I've actually been running quite a few climate simulations from in this period to assess the impact of this variability. And I do get different TCR actually, but I'm also running one from here. And it's interesting because you've got 1% CO2 run and the sea ice increases because it is driven by the ocean emission.
No, I just wonder about the Arctic sea ice in this, because normally the global temperatures are more correlated to the Arctic sea ice. Do you see some changes as well, or did the Arctic sea ice stayed constant?
So the Arctic sea ice does not respond on these very short time scales to the burps, but it does respond to this average difference in global temperature. So the Arctic sea ice volume is reduced in a manner that you would expect, given almost half a degree global increase.
Okay, thank you, Ed. Thank you to all the speakers this morning. It's now off to lunch, Churchill College. We're due back here at 2 o'clock, I think, is that right? So can I ask that we try to get here at 1:55, because inevitably people will be delayed. Apparently, this room is not locked, okay, but apparently it is standard practice for people to leave their stuff here